Okay, so we're going to work on this problem. We have the relative frequency distribution given by table 1 represents the heights of the pediatrician's 3-year-old female patients. The raw data indicates that the mean height of the patients is 38 inches, and the standard deviation is 3.17 inches. Draw a relative frequency distribution of the data and then comment on the shape. So if we were going to do that, then obviously here's the picture of it. I would say that this, for the most part, looks normal. It's not perfect, but at the same time, it does not need to be perfect to be normal. And so with that being said, the next thing says draw the normal curve with a mean of 38.72 inches relative to the frequency histogram, I'm sorry. Compare the area of the rectangle of the heights between 90 and 40 and 40.9 inches to the area under the normal curve for the heights between 40 and that. So what I'm going to do is I'm just going to draw it on the actual picture. So if we were to draw a normal curve, it would go something, or if we were to draw like the kind of shape of this thing, it would go something like this. Okay. It's not perfect, but at the same time, I'm doing it by hand. And then, so this would be the 38.72, and then 3.17. So that's 3 standard deviations away from that. So that's going to be 1, 2, 3. It's like right here. Not 3 standard deviations. I'm sorry. 3 away from it. So we add about 3 to 38. That's about 41 point something. Okay, here is this. This is the mean plus sigma. Oops, I drew alpha. Oh no. That's the mean plus sigma. And then I've only drawn it on that side, obviously, because I want to make sure that because we're only looking at the areas from 40 to 40.9. And then it wants us to, so we're looking from 40 to 40.9. That would be right here. Okay, so I've shaded that in. I mean, if you look at it, it almost fits that whole entire rectangle, right? Like, it's only missing this top portion, and that's not very much data. Um, and so I think we can kind of make the conclusion that, yeah, this does fit the normal curve, um, and that it does seem to almost fit that relative frequency for the normal distribution of this thing. With that being said, let's look at the next slide. We have this one, and so it says the area under a normal curve. Suppose that the random variable x is normally distributed with a mean of of mu and a standard deviation sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristics described by the interval of the values, or the probability that a randomly selected individual from a population will have a characteristic described by the internal values. So kind of just to reiterate real quick, because the area under this, based on this relative frequency for here, oops, I'm sorry, not that one. That would be for here, is 11%. We would expect that under this curve, if you were to do from 40.9 to 40, it would be about 11% as well. Okay, that's basically what that slide's saying. So that the height between those is about an 11% chance of any randomly selected person being between 40 and 40.9 inches. So we have one more thing to do. We have one more example problem, so let's do it. The serum total cholesterol for males between 20 and 29 is approximately normally distributed with a mean of 180 and a standard deviation of 36.2 based on a survey. Draw a normal curve with parameters labeled. So let's do that. I'm going to zoom in a little bit. So the first things first, we're going to draw, this is part A. best, we have something that resembles this. Hopefully it's about symmetric. It might not be, but here's our mean, and this is 180. One standard deviation, we'll go 2. This is our mean plus sigma. This is our mean minus sigma. And we did do this on the first test, so if we do 180 plus 36.2, 216.2, so this is 216.2. If we add 36.2 to that, that's mu, oops, whoa, that is mu plus sigma, 2 sigma. Plus 2 sigma, which is 252.4. And then obviously we can go backwards. If we do 180 minus 36.2, 143.8. And then we'll do it again, minus 36.2. Whoa, what did I do? Oh, 36.2, 107.6, minus 2 sigma, 107.6. And so I think that's all they want for that. An individual with cholesterol greater than 200 is considered to have high cholesterol. Shade the region under the normal curve to the right of 200. So, I mean, we've got 180, we've got 216. Let's just estimate 200 is about halfway-ish, maybe a little bit more towards 180. So if we have that, the red region will be the area of people with high cholesterol. And then suppose that the area under the normal curve to the right, so the area of this is 0.2903. So there's a 29% chance that you fall here in this curve. Then how will you provide two interpretations? So there's a 29% chance that this is a 29% chance that a randomly selected person has high cholesterol. So obviously, if you randomly pick any person, you know, the majority of people are going to be normally distributed around here. And so if you get picked when you have a 207 cholesterol rating, then you will be in that 29% chance of people who are considered to have high cholesterol. Another interpretation is that if you had 100 people and you randomly picked 100 people out of a population, you would have about 29 of them who did have what we consider to be high cholesterol. I hope this helps you understand these things. Have a good day. Talk to you soon, guys.